Hello people, welcome back, and today we're going to be looking at some of the topics for your paper 1 chemistry. We're going to be looking at how they marry up with the AQA spec and the Carburetor books. But before we get into that, shout out to this guy who's subscribed to the channel, and if you haven't done so but you find this useful, what are you waiting for? Do it! So let's jump into this right now.
It was a nightmare.
Activate.
Okay people, so we're going to start looking at this chemistry warm-up PowerPoint I've created, where we're going to be looking at the different topics of AQA and compare them with the Carburetor books. So we're going to start with atomic structure and the periodic table. We're going to try to make this into short videos so it's easier to digest. So let's get on with it. So to start, what we got here is that 4.1 atomic structure in the periodic table is split into C1 and C2 in the Carburetor books. So in C1, we're going to learn that you got to familiarize yourself with the periodic table. Okay, so what we see over here in blue is your metals, and what we see in green is your non-metals. Okay, so you need to learn the periodic table. You got to get yourself familiarized with the first 20 elements to start with. You got to make sure that you know the symbol for them, so when you look at them in the periodic table, you know exactly where to go. Okay, you not need to memorize anything. As long as you learn how to read the periodic table, you'll be fine. Right, so then we got that each element has its own unique letter or combination of letters. So for instance, carbon's got a C, and then we got helium, copper, and hydrogen. However, symbols can be initials from many different languages depending on when and where they were discovered. Okay, so if you have one of them, it will be a capital letter, so single capital letter. But if you got two, the first one will be a capital and the second one will be a lowercase. Okay, a lot of the time you might get marks deducted for not writing the symbols properly. Okay, it's an easy marks there. Now when looking at molecules, these are chemicals that are made from two or more atoms. So we can have, if these molecules can be of the same atom, which are molecules of an element, like the ones that we have here, these two carbons and these three carbons joined together. And we can also have, if they are from different atoms, they are molecules of a compound. Okay, so we got this one here, you got two or more different types of atoms. That is a compound, that compound, this is a compound, 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 and compound. You get the idea, okay? Now, compounds are made when two or more chemicals react in a chemical reaction, and these chemical reactions can be represented by, you have the word equation. For instance, you got sodium and chlorine, which makes sodium chloride. You have symbols, equations like Na plus Cl2 and NaCl, and this will be the symbols. Okay, now over here chlorine is just Cl, but because chlorine gas is normally found, it's a diatomic molecule, you're always gonna find them in twos, and obviously we need to balance the equation. Okay, you balance the symbol equation to make sure that you have the same amount of atoms in one side of the equation and in the other side of the equation. Okay, reactants and products. Now, if you're in a higher tier, you gotta be looking at ionic equations as well. So for instance, in this case, if you got a chlorine that's got a negative charge, you take away one electron, it becomes a chlorine atom. Same over here, chlorine atoms, you join them together and then you get chlorine gas. Okay, or you could do it in the following way, which means that two chlorine ions lose two electrons, one each, and they end up making a chlorine gas. You gotta familiarize yourself, but you're gonna see a little bit more of this when you get into electrolysis. Okay, now balance symbol equations. Count the number of atoms in each side of the chemical reaction, and again, this is just the way I do it. I find it the easiest to do it. Number 2, make the small number equal to the big ones, and number 3, always start balancing hydrogen, oxygens, and then you do anything else. Right, so over here we got two hydrogens and two oxygens, so we got hydrogen gas and oxygen gas reacting to produce water. However, as you can see, this equation is not balanced because you don't have the same amount of atoms in one side, I mean after the arrow in the products and before the arrow in the reactants. Now we got hydrogen, oxygen, water, and this will be your word equation and your symbol equation. Okay, now so if we add another one there, okay, that means that you need to add another one here, and now we'll have a balanced equation. You got 4 hydrogens in reactants, 4 hydrogens in product, 2 oxygens in the reactants, and 2 oxygens in the product. But how did that happen? So that's what we're going to be looking at right now. First of all, we count the number of atoms in each side in the chemical reaction. So over here I tend to do the whole process just to find out where I got things wrong. just in case. So we got hydrogens, first start with hydrogen, then oxygens, and then anything else. So here we go, we got 2 over there, 2 over here, 2 oxygens and 1 oxygen. Okay, make the small number equal to the big one. So we're gonna make the oxygen down there on the right turn into a 2. So what we can do is that we can multiply the whole thing by it. So we already started with the hydrogens, oxygens. So if we look at that, we got a 2 there. That would mean that that oxygen is going to be multiplied times 2. So now you got 2 oxygens on the right and 2 oxygens on the left. However, because that 2 is before the molecule, it would also multiply the amount of hydrogens. And that means that this hydrogen here is also going to be multiplied by 2. So you're going to have 4 hydrogens instead. So oxygens are balanced now, but the hydrogens are not balanced now. So what we're going to do, we're going to multiply that hydrogen times 2. And then we're going to get a 4. And now we have 4 and 4, 2 and 2. Now we got the equation balanced for the combustion of hydrogen and oxygen to form water. Okay. In some cases, you probably see this here as gas when it condenses and turns into liquid, but I think going for gas will probably be the safer option. Okay. Okay, so what I have here is just a couple of things you got to look at when you are balancing equations. First of all, you can only add big numbers to the left of the molecules, okay? That big number will multiply every single atom that you have in there, every single element, and you're looking at the upper cases, okay? Now, some students get that confused and they when they see symbols like K, with like Ca, they normally think there's 2 different elements, but you got to be wary of that. It's only one element, and that will be because it's got 1 capital letter, okay? Now, this little number down here, you will never add a small number to the right of the molecule, okay? You will never do that. Every time you try to balance an equation, you add in a whole molecule, not the structure of the molecule, okay? Now, the small numbers tell you the number of atoms of the element right next to it. In this case, will be oxygen. Now, the big numbers to the left of the molecule will not multiply past the plus sign. Okay, so these 2 will multiply everything in here except once we pass this sign over here, okay? So small numbers to the outside outside the bracket of the molecule will only multiply the elements inside the bracket. So these 2 over here is only going to multiply the hydrogen and the oxygen, just like it does in maths, okay? Then we got this big number here. If the big number to the right of the molecule, it will multiply everything, including what's inside the bracket. Okay, so we have 2 to be times calcium, 2 times nitrogen, 2 times the oxygen. And let's see, so if you over here we got a little number 3, that means there's 3 oxygens, but because you have a 2 outside the bracket, that means that there is 6 oxygens instead. And because you have a 2 over here on the left, it means that you don't have 6 oxygen, you actually would have 12 oxygens because you're multiplying everything by 2. Okay, so when counting the number of atoms, always separate the numbers of atoms in each molecule, even if they are from the same element. That way it is a lot easier for you to make calculations once you're doing the multiplication, okay? So in this case, if these 2 are reactants, I've written down that you have 3 oxygens in this molecule and you have 2 oxygens in this other molecule. The same with the hydrogens, there's 1 hydrogen in this molecule and there is 2 hydrogens in that molecule, and over here you will continue to the products, okay? But we need to keep them separated. Right, there we go. So don't be lazy, write the steps, but remember the process, and it makes it easy to backtrack and find out where you made a mistake if they're not adding up, okay? However, most of the time balancing equation questions in your exams will equal to 1 point or maybe 2 points. So what I would normally do is that I will leave them undone. I will continue doing the rest of the paper, and if you have time, you can come back for those questions, okay? Because a lot of the time you spend more than a minute, depending on your skills on balancing the equation. You probably spend more than a minute trying to balance an equation, and it's only going to give you 1 mark, okay? So you want to make sure you tell yourself that you're going for 1 mark per minute. So that's the pace that you want to work at, okay? Right. So according to the AQA structure, students will be supplied with a periodic table in the exam and should be able to use the names of the symbol of the first 20 elements in the periodic table, the elements in group 1 to 7, and other elements in the specification. Name compounds of these elements for given formula or symbol equations. So write down the equation for the reaction in specific in this specification and write the formula and balance chemical equations for the reactions in the specification. Okay, so this is the things that we covered right now. This is the things that you want to look at when you're doing your revision. Okay, for the higher tier only, write balance half equations of ionic equations where appropriate. And again, like I said to you guys, you're going to be seeing a lot more of that when you do your when you do the topics on electrolysis. Okay, and read those reactions. Now, mixture consists of two or more substances that are not chemically bonded and their chemical properties remain unchanged, whilst in a compound the substances are chemically bonded and the properties of the reactants change as they form a new product. Mixtures can be separated by the following separation techniques: filtration, crystallization, simple distillation, fractional distillation, and chromatography. Okay, now something important for you to remember here is that the mixtures are combined but not chemically bonded, whilst a compound are combined and they are chemically bonded. Okay, so they make something absolutely different to the reactants. Now, filtration, the solution passes through a semi-permeable membrane which only allows molecules of a specific size to pass through. Whatever goes through it is called a filtrate, and anything left behind is called a residue. Okay, this is pretty much self-explanatory, but there are situations in which you'll be asked to create a practical method in which you might need to use more than one separation technique at a time. Okay. Now, crystallization and evaporation. The solution is heated. Once the temperature reaches the liquid, the boiling point of the liquid, this will evaporate and the solid will be left behind in the evaporating basin or dish. Okay. Now, this is normally used if you're just looking for the solid and you think that the water is a surplus. You don't really need the liquid, or it could be any liquid, but this is what you would use. Okay. In this case, if it's water, you just want the water to evaporate and you want to have, I don't know, maybe salt crystals, and that should be enough. But if you're looking to actually retain the liquid, you will be using a different technique. Okay, and this is where simple distillation comes from. The solution is heated. Once the temperature reaches the boiling point of the liquid, this will evaporate and travel through the condenser, turn back into liquid, and then collected. The solid will be left behind in the conical flask. So if this was salted water, all the water will evaporate, turn into steam, travel through the condenser. Over here we have a water jacket with cold water, and then all that steam actually turns back into a liquid and is collected, and you will have the salt left behind. And in this case, unlike evaporation and crystallization, you actually want the water, so you collect the water, and that's the difference between simple distillation and evaporation. Okay, then you also have fractional distillation. The liquid mixture is boiled in the fraction in the mix with the lowest boiling point will evaporate and travel all the way to the top of the fractional column. And so, say for instance, we have an example of an alcohol mixed with water, and it passes through the condenser, then evaporates. So this part over here will be essentially the same as in normal distillation. So if you have alcohol and water, some alcohols will evaporate about 78 degrees Celsius. So once they are boiled up, everything boils up, the water and the alcohol, but as you travel up the fractional column, it gets cooler and cooler. So it's not going to be hot enough to keep the water as a vapor, so it will condense and drip back down. However, it is still hot enough for the alcohol to remain as a vapor. So the alcohol will continue progressing as a vapor, get condensed and then collected, and the water will just drip back down because on the top of the fractional column is not hot enough to keep the water as a gas. Okay, so moving on from that, you got paper chromatography. It separates substances from a mixture according to their solubility and affinity to the mobile phase or solvent. Okay, the higher the spot travels up the stationary phase, the paper, the higher the affinity of the substance to the mobile phase. So the mobile phase would be the solvent. It could be water, it could be alcohol, it could be any other type of liquid, and then the stationary phase is always going to be the chromatography paper, which can be of different combinations of materials. Okay, right. So and students should be able to describe and explain and give examples of specific processes of separation and suggest suitable separation and purification techniques for the mixture when given appropriate information. Okay, so two things that you might get here in regards to practicals. They might ask you how the fractional distillation of alcohol and water works, and they might ask you how to separate have dry salt crystals from rock salt and you might want to explain the process, and that could very well be a 6-mark question if you're doing a foundation. Okay, you might be even be given a diagram to work with. Also, we're going to be looking at how the model of the atom has evolved over time. So new experimental evidence may lead to scientific models of the atom being changed or replaced. So first we have John Dalton in 1804. You don't need to remember dates. You don't need to you kind of need to remember John Dalton, so you know that this is his specific design. He said that matter was made of tiny spheres that could not be broken up. He concluded that the electrons must have come from the inside of the atom, and that they must have been embedded in a positively charged cloud. Okay, so this is what we call the plum pudding model, because you have a positive cloud with the electrons embedded into it, and when looking at it from the top, it does look like a plum pudding, according to the popular dessert at the time, at the end in 1804. Okay, so Rutherford's experiments by firing alpha particles, positive particles, through a gold sheet. Some of them were deflected and changed trajectory, meaning that atoms were mainly empty space and that they had a positive charge in the center, and that's what they call the nucleus, and they were called protons. Okay, so what we had here is that we have the source. Alpha particles were fired up through the little tiny gap in the lead box, and as they go through, after they collide with the with a gold foil, a vast majority of them actually went straight through. Some of them changed trajectory, meaning there must have been something that they collide with that made them change direction, and the ones that hit dead on straight, they actually bounced back. Okay, and this led to the discovery that the atoms were not actually solid spheres or spheres of positively charged and electrons attached to it, but instead it was mainly empty space, and they have something positive in the middle, and that was the nucleus. Okay, and it was the dense part. Okay, right. So a student should be able to describe why the new evidence from the scattering experiment led to the change of the atomic model, and the difference between the plum pudding model and the atom and the nuclear model of the atom. Okay, so you might be given the diagrams of the plum pudding and the atomic model of the atom, and you basically are doing spot the difference in that. One has nucleus, the other one doesn't have nucleus. One has protons, the other doesn't have protons, and one of them's got shells, the other one's got the shell, electrons embedded into it. It's easy marks on that. Okay, if you're doing foundation, they might give you a diagram. If you're not doing foundation, you might not get a diagram on that. Okay, so then we're looking at the atoms are made of subatomic particles called protons, neutrons, and electrons. Okay, so we got the protons have a charge of +1 and they have a mass of 1. The neutrons have a charge of 0 because they don't have a charge, they're not positive, they're not negative, but they have a mass of 1. And the electrons are negatively charged with a charge of -1, but they are so tiny that we can just say that their mass is 0. Okay, you need 2,000 electrons, approximately 2,000 electrons, to make the mass of 1 proton or 1 neutron. So we say that they're so small they don't actually influence the mass of the atoms itself. Okay. Now, over here we have the electronic structure of an atom can be represented by by numbers or by a diagram. For example, the electronic structure of sodium is 281, or showing 2 electrons in the lowest energy level, 8 in the second energy level, and 1 in the third energy level. Okay, so what we got here is that we got 2, 8, and then 1. That will be the electronic structure, okay, electronic configuration of it. Atoms can be described as the smallest particle of a chemical element, and in this case we see that in the middle, in the nucleus, we have the protons and the neutrons, and in the shells or energy levels we have the electrons. Okay, you always gonna have the same number of protons and same number of electrons because they cancel each other out. That's why atoms don't have a charge. So the atomic number down here that you can see in the periodic table, a lot of periodic tables will be different. Okay, some of them will have the smallest value numbers at the top, the big ones at the bottom. They could be anywhere, they could be decimals, but in general the smallest value number is going to be the atomic number, and this number tells you the number of positive protons in the atom. If, for instance, in this case carbon has got 6 positive protons, it should have also 6 negative electrons, which will cancel the positive charges, giving the carbon the overcharge of 0. Okay, now the mass number at the top, that tells you the amount of protons and neutrons that element has. Okay, so for instance, in this case the mass number is 12, and if we know that it's got 6 protons, 6 take away from 12 is 6, so it should also have 6 neutrons. Okay, Right, and obviously the majority of the mass of the atom is concentrated in the center, okay? Now, the atomic radius of about 0.1 nanometers, and the radius of a nucleus is less than 1/10,000 of that of an atom's about 1 × 10 to the minus 14 So they are very, very, very small, okay? This is something you got to take in mind. You won't be asked too much about it. Maybe they might ask you the difference in size between which one is bigger, an atom or an ion, and clearly you will have to say that the ions are always smaller because they have one less shell, they lost electrons and whatnot, and that will probably be in the case of metals, really, okay? Right, so moving on from there. Ions. Atoms are neutral because they have the same number of positive protons and electrons. So if the atom donates electrons, it becomes positive ion, and that will be an atom. Take away an electron equals a positive ion. If the atom receives electrons, it becomes a negative ion. So we got atom plus electron equals negative ion. Now, if the atom donates electrons, it becomes a positive ion, and the way that we record that is because this is the way I tend to teach it to my students, is that cat got paws, and paws means positive, okay? And the name of the positive ions is cat ions. So cat ions, cat got paws, those are positive. Now, on the other hand, we have the anions. For me, onions are negative. So if you change the O from onion, you get to an A, you get anions, and that's a negative for Mr. Rosales, so definitely not, okay? So this is what we got there. Negative ions are anions, and the positive ions are cations. Right, so isotopes, atoms of the same element with different number of neutrons are called isotopes. If this difference can influence the physical properties of a substance such as density and radioactivity. However, the chemical properties will remain the same, okay? In this case over here, we got three different isotopes of carbon, carbon 12, 13, and 14. They have the same number of protons, same number of electrons all across. The only thing that changes is the number of neutrons, and it might change slightly the physical properties of it, not the chemical ones, okay? It might lead it to melt or boil half a degree higher or half a degree lower. Again, physical properties. We also have the ones for hydrogen. You got hydrogen 1, 2, and 3. You can see they all have one proton, they all have one electron. The difference lies within the neutrons. 0 neutrons, 1 neutron, 2 neutrons. And again, this is something that can be related to the physical properties. When we're talking about heavy water, we mean that most of that water, or a high percentage of that water, will have the hydrogens 3 or 2. Meaning that because they have more neutrons, the atomic weight of that hydrogen ion is atom is slightly bigger than the normal one here with no neutrons, okay? And it will alter the physical properties, meaning that water might boil slightly higher or slightly lower, okay? Different isotopes have different relative abundances, which means that some isotopes are more naturally abundant on Earth than others. Chlorine 35 has a relative abundance of 75.76%. That means that from all the chlorine in the world, about 75.76% would be chlorine 35, whilst 24.24% would be chlorine 37, okay? Now, that will make up 100% of all the chlorine in the world, and an element's average atomic mass is actually a weighted average calculated from these values. So for an average atomic mass of chlorine, we will have 0.7576 times 35. That will be these values over here at the top, and then you have 0.2424 times 37, the values of these ones over here, okay? And we got 26.5, 8.96. We add them together, we get 35.47, and then we round it up to 35.5. When you look at the periodic table, the numbers in the chlorine will be 17. That will be your atomic number. That's the smallest value number. That's the number of protons and electrons, and then the combination of protons and neutrons would be 35.5, although you can't really have half a proton or half a neutron, but because it's an average calculation of all the isotopes, we end up with a decimal point in there, okay? So students should be able to use the nuclear model to describe atoms. Students should be able to calculate the number of protons, neutrons, and electrons in an atom or ion given the atomic number and mass. Students should be able to relate to the size and scales of atoms of an object in the physical world, and students should be able to calculate the relative atomic mass of a given element, the percentage given the percentage abundance of the isotope. Okay, so these are the things that AQA is more likely to be looking for testing in one of their papers. Okay, straight to the point. So that's all we got for C1. Make sure you click on the next video so we can look at C2. And if you do have any questions, please drop them in the comments and I will get back to you as soon as possible. Okay, as always, knowledge is power. See you in the next video.